Okay, so maybe it's live going here. I guess this is live. It doesn't, it's not showing picture. Okay, wow. Okay, so I guess we're live. Okay, cool, yeah. Right, so anyway, I was doing the thing where you, you look at the, for like a small, yeah, okay, so like we were, I think we're trying to do the thing where, yeah, so like we're trying to do the thing where like in a small like in a small neural net, it's like, you train it on images. And, and then it's like, where are the images in the weights, right? And then, and then it's kind of like the observation, there's an observation, which is that there's observation, which is that, so like when you start the neural net, like you randomly initialize it. And so there's kind of this observation, which is that, like if you're only training on like a single input output, for instance, then probably most of the parameters in the neural net are going to be, like pretty close to their initialization. And then like, but then if you have lots of input-output constraints, then the parameters, so it's like, I mean, it's like if you randomly initialize a neural net, it's like, okay, there's this random initialization is completely independent of any data set. So yeah, so I guess we're trying to understand the transition between random initialization of all of the neural net parameters and like how it comes to be like correlated with the, or like how it comes to be associated in any way with the training data. And so we were like, you should look at like a super small, you should look at like a super small neural net. Like, so this is what we have here. So this is like 2 inputs, hidden layer of 2, 1 output, ReLU activation. And so then it's like you can represent the entire you can represent the like the output activation. I guess kind of, I mean, like we're ignoring like error. But anyway, you can represent the entire output activation. I guess like in this way, does this make sense? Cause does this one make sense? Cause like I'm not seeing necessarily maybe the output unit doesn't have a bias. Yeah. Okay, so, but yeah, okay, but like you can build it up or something, so it's like, it's like, okay, so it's like this expression is the first activation, or like the, so it's like it's the first, it's the 2-2-1 thing. And then we're doing ReLU, so it's this max 0, this expression over here. X1 is the first input, X2 is the second input, and then the weight. I think the indices on the weights, it's like, this is the first layer, the first unit, and then the first input. This is first layer, first unit, second input, yeah, it's like, I mean, the indices are super annoying. But anyway, that is the expression for the first neuron. And then it's the exact same for the second neuron. So those are all the neurons in the first layer. And then we go directly to, I see, okay, so like this whole thing is the, yeah, so it's like, this is the bias for the second layer, and then this is the weight in the second layer. First neuron, there's only one neuron, first input to the second layer, and then this is the thing, yeah, okay. So, yeah, I mean, obviously, like, symbolically, this is, yeah, I mean, like, you have, like, crazy nested, like, nonlinear expressions and stuff, so, and people don't like that. People don't, yeah. I guess, like, basically when you're writing it, symbolically, it gives you a tree. Yeah. Okay, but anyway, so let's look at the derivative. So this is saying we don't have loss function, so we're just looking at how does the activation for the output, which is this entire expression. We just picked one of the parameters, so we picked the weight in the first layer. For the first unit in the first layer, connecting the first input to the first unit. So it's like W11111. And yeah, and so like the derivative for the ReLU is like it's just if the input to the ReLU is not negative, then the derivative is 1, and if it is negative, then it's 0. So I think that's what this little symbol is supposed to represent. So this little symbol, okay, yeah, so it's like, let's see if we can try to make sense of this thing. I think like already I can't make sense of it because like shouldn't okay, so let's see if we can try to make sense of this. Okay, yes, I will like try to write stuff over here. That's cool. People like writing stuff. I have to wait for my tablet to turn on. Okay, so it's on now. Okay, so I have to beg OneNote to let me scroll some more. So I have to put that thingy there. Okay, so then it kind of lets you scroll. Thank you OneNote for letting me scroll. What was I doing? Oh yeah, okay, so like the architecture that we're looking at is this thingy here. So we're doing they call it x1, x2, and then you have like 2 units that are ReLU, and then this guy, okay, and then so these are all like ReLUs, and then we're looking at this connection. This is weight 111, like weight. So in the first layer, it's the first unit. It's connecting the first input. So it's weight, yeah, okay, so like, and then this is, what are they calling this? They're calling this output. Yeah, so like this, we'll call it Y. Right, and like Y is like, just defined to be max. This is ReLU of 0, and like yeah, the dot product thingy plus the bias. Okay. Right. Okay, so then so like we're trying to manually compute this gradient with respect to this. This weight is 111. Just to be super annoying. Like, if you don't have 45 different subscripts, like, you're not doing real stuff, so I will edit this to make it better. Okay, so let's see. One perfect. Oh, it's still messed up. That's weird. Okay. Oh yeah. Okay. So it's like we want to. Okay. So it's like how do you differentiate this thingy? Yeah. I think it's like you have to, because you have right. So I mean, like in general. Okay. Yeah. So like in general, if you have I mean also it's like, yeah, it's not like technically differentiable or whatever, but like we don't care. So it's like in general, if you have like max 0 x, and this is and then you're like, what is no, let's see, did I mess that up somehow already? Yeah, I think I did. Max I think I'm already messed up. I don't know how to maybe looking at the 10H would be easier. Well, I mean, even the 10H expression is weird, because like should not there be like a 10H this is our thing, man. Okay, so if you listen, if you do like f of g of x, then you're like the dy dx thingy. It's like it's just yeah, it's like df dg dx, right? Like this is basic calculus. This is like yeah, it's like basic calculus and stuff. Okay, so we're doing good on basic calculus. So then like but if the thing is dang man, why does it do this? This is weird. So if you have y, so like but if you have like y is max 0 versus x, right, I mean that's not really a function composition. Yeah, I think I'm too confused here about this. Right, I mean it's gonna be like a thing. It's gonna be like dy dx equals, like it's gonna depend, like if x is less than 0, then like the derivative is 0. x greater than 0, then it's just... Then what is it? Yeah, so, okay, so I don't know how to differentiate a ReLU, but that's fine. Well, I mean, theoretically, this is what this is supposed to be doing. So, yeah, let's see. Okay, so it's like, let's see if this one makes more sense, though, maybe. No, this is like not making sense to me. I think, like, what is the nesting? So this is like this one thing. Right, I believe this function is the step function, so it's like, or like this, yeah, it's like the step function. It's saying like if the expression inside is, greater than 0, then it's 1, otherwise it's 0. Maybe. 112. Okay, so it's like this expression is the activation for the first neuron and the first layer, right? Yeah. Okay, so it's definitely the first neuron and the first layer. What the hell, man? But all of this is inside of this function here. This expression is the activation for the second neuron. And then that weight is the second layer, the first unit, the second weight, second layer, first unit. I don't understand what it's doing. Oh, I see. Okay, so like it's putting... I mean, like this, like if this were a max 0, then this whole expression is just the activation for the output unit, right? Yeah, because you have like P21 plus 211 max 0 11 112 x2 w212 max 0 b12 121 x1 122. Yeah, okay. So this whole expression is just the current activation for the output unit. And then this expression is the like derivative for the first unit and the first layer. That's like the derivative of the first unit and the first layer times x1. Okay, I think that almost kind of makes sense, maybe, probably not, but okay, so like what it's, yeah, okay, so I had to delete all of this stuff. Okay, oh dang, is that gonna work? Oh sweet. Okay, delete that, delete this thingy, delete that thingy. Okay, okay, so like the thing it's doing is so it's saying like, yeah, so it's like you have this output unit, and then you have this activation, you have this activation, then you have x1, then you have x2, and we're trying to compute the output with respect to this is weight 111, so that's weight 111, and then this is output, and these activations are all like, you know, ReLU, and and like this so like this weight is W second layer to second layer, first unit, there's only one unit, but it's, and then like that, and then this one is second layer, first unit, second input. Okay, so those are the two weights going on. And so let's see if we can like maybe make sense of this. I mean, the thing is I don't know if this is actually correct or not. This computation, because no, that did not help the situation. Okay, so okay, so saying like, yes, okay, so like if we call this the output, and you know, output with respect to W111, right? Like that's the whole thing. So I mean, like the normal way that you would do this is you would just like, you would compute this intermediate. Yeah, by the way, I mean, like this is all a chain. Like it's not a very interesting example, I guess, but it's like kind of a pain in the ass. But yeah, so I mean, like to compute, so what you're saying is, you're saying like, okay, you know, the old partial derivative, you know, it's like I increase this weight by an infinitesimal amount, and then it's like, what is the ratio, or like how much, what is the response of the output? And the way you normally do this, like with backpropagation, is you do these intermediate thingies. So like what you would do is you compute the if we call this activation, like I guess keeping with the scheme, it would be like, if we call this activation it's the first hidden layer, and it's the first unit. Yeah, I don't like doing this because there's too much I don't like using so many like indices, subscripts, because it's impossible to like understand what's going on. But anyway, normally you'd be like okay, if I know how the output changes with respect to this activation, then I can compute how this activation changes with respect to this weight 111. I mean, yeah, no, I gotta not use subscripts because they're terrible. And then it's like, you know, it's like calculus or whatever. It's like, yeah, you can just, you multiply these two quantities, and then it gives you the thing you're trying to find, which is the response of the output on this parameter. And yeah, so yeah, and like we're trying to map this over to this symbolic expression, because like it's in the symbolic expression we don't have a concept of the activation. Like we're trying to write everything in terms of the parameters and the inputs. Not really for any particular reason, but I think like mainly because it's, well, nah, it's but anyway, so yeah, okay, so like what would be this expression like over here, right? So yeah, I mean, right, I mean, A11 is this, yeah, okay, so let's try to compute that, right? Okay, so like A11 by definition is ReLU, which we're writing as max 0. And then and then it's just a linear combination. It's the parameter we're interested in, which is this one, and then the other one. So we'll see, we're in the first hidden layer, the first unit, the second input, and then I was going to delete that. Okay, right. So, okay, so we're trying to differentiate this. We're trying to, yeah, we're just trying to differentiate this expression with respect to this input. Which yeah, like I don't know how to do. I mean, it's like, yeah, how do you do this? I mean, like, yeah, no, I don't know how to do that. Yeah, this is a fundamental problem because I don't know how to differentiate a ReLU. Ha! I thought, I don't know. Cause, I mean, wouldn't it just be like, oh yeah. Wouldn't it, okay, so wouldn't it be like this guy? Okay, so first of all, let me define this. I think this is the heaviside function according to the AI that wrote all of this. Ha! Yeah, so like this one is defined as like, it's like, it's a function of, I think it's just like a function of an input, and then it's just like, it's just 0 or 1, so it's like if it's greater than 0, then it's 1. And then if it's less than, or I guess equal to 0, it's 0. Okay, and so I think that's what we need, because I think what you're going to do is you're going to say like the partial, or I don't know, yeah, the derivative of A11 with respect to W111, and this expression over here is, I think you put this entire, let's see, because if this expression is negative, then this whole thing is 0, and so the whole thing is 0, right? And then like, but if this expression is positive, then this whole expression just becomes this expression, and then it just becomes the derivative of this expression, right? Which would be x1. So I think that's why, yeah. So I mean, like you just so I think that's, yeah. You just like you copy this expression into the thingy here. Like theoretically or some stuff. So that, oh dang man, that gets copied to there. And then you do, and then it's just the derivative of this interior expression, which gives you the x1. Okay, so do we have this happening anywhere over here? Also over here, like we have bias. Like I wasn't using the bias, but that's fine. Okay, so yeah, so like here's that part, right? This is the part we just fixed. Okay, so this expression, the x1 heavy side, b11 111, yeah, that's this. Okay, so this is what we just figured out. So this part is right, so this part is the partial derivative of the activation in the first layer with respect to w111. And then it's and then this expression within this heavy side is just the activation for the output unit. And then the only other thing is this weight. Okay, so like, does that make sense? Cause I mean, like, you know, like it's saying like in the gradient update, if like if we're just concerned with, say, like making the output activation increase, like we don't have loss function or whatever, that's fine. So what is saying? Well, no, I mean, okay, so I mean, it's just saying the sensitivity of this output value to this parameter 1111111 is the let's see, does it make sense? It's like, okay, well because, okay, so like so I mean, like if you tweak this parameter, right, you're going to make this activation go up by x1 amount, and that is this part. Yeah, because it's saying like if this activation is 0, then increasing this parameter doesn't have any effect because the activation is 0. So that's what the heaviside function was saying, but then otherwise it's saying like if the activation is positive, then this heaviside function is 1, and so you're actually just increasing this activation by x1. So that that makes sense, but it's kind of like a conditional yeah, I mean, like the Heaviside function is like a conditional kind of thing where yeah, like, okay, but anyway, okay, so I think we understand that part. But then we need to understand like this connection. Because the rest of the connection, right? So I think like the rest of this expression is just saying like if the output like on x1 x2 and you do the forward pass and this is a 0, you know, then it's like infinitesimally it will always be a 0. So that's what this is checking. Like this is like a conditional checking, and it's just saying like, you know, if the total activation in the forward pass is 0, then the gradient or like the amount that the output is going to change is also 0, because although I mean, like, you know, like that's technically I mean that's the weird thing, because the ReLU and you have like a non-differentiable thingy. Okay, but then like if this, so okay, so but then if this activation is positive, then this evaluates to 1. This evaluates to 1, or like, well, I mean not. Assuming both of the Heaviside functions evaluate to 1, then what you get is just this x1 w11 term. Yeah, but shouldn't you pick up a 211 term? Or, oh no, you should only pick up the 2. Okay, alright. Okay. That makes, wait, does that make sense? I'm not sure that, okay, so what you're saying is you're assuming this activation is 1. You're assuming this you're assuming this activation is positive. You're assuming this activation is positive. And then you're saying like, I'm going to infinitesimally tweak 11111. And how much is that going to increase this activation? And what this is saying is that what's going to happen is it's going to go up by x1 times 211. And I think that makes sense, right? Because like you increase this guy, you know, you're increasing this activation by x1, and then you're picking up this 211. Okay, so I think the parsing of this expression is like this one is checking, right? So like this is the actual gradient like value if everything is 1. Everything else is checking for like zeros. Like this is checking if this activation is 0 or negative. Yeah, because like if that activation is 0, then everything is 0. And then this expression is checking that everything over here is 0 or not. Yeah, okay, so like we kind of figured that part out. Yeah, but I was like, right, so, that is for, 111. But I mean, like, so like, and the uh, gradient update. I mean, like, this is the. I guess it's like, because I think we saw in some like, if you look at the parameter trajectories, like, the magnitudes of the gradients, like, can go up and down. Like, you can get like oscillatory behavior even with a single like even with a single input output pair. And I think we were like trying to figure that out, why that would happen. Yeah, I took a break there. Took a break.